We have seen rules for the sums and products of the roots of quadratic equations. Let's now have a look at cubic equations and also more general polynomial equations. So for the cubic equation, ax cubed plus bx squared plus cx plus d equals 0, with solutions or roots x1, x2, and x3, we have these results. The sum of the three roots is equal to minus b over a, which is exactly the same as it was for quadratics. The product of the roots is minus d over a. And that is similar to the one for quadratics. It's the constant term divided by the leading coefficient, but notice that the sign has changed. And we can also get another one. We can also get the sum of the pairwise products of the roots. So that is multiplying them together in pairs and then adding all those products up. This one is equal to c over a. Now you will notice that they're all over a. And then the other thing to notice is that depending on how many things we're multiplying together at once, in this case we're multiplying one thing together, this time three things together, and in this time two things together each time. That's how far back we have to go to work out what the numerator of the fraction is. So when we multiply one thing at a time, we go back by 1 to get b as the numerator. When we multiply two things at a time, we go back 2 to get c as our numerator. When we multiply three things at a time, we go back 1, 2, 3 to get d as our numerator. We also have this sign going on here. Now the sign is to do with how many steps we go back as well. The sign is always going to be negative when the number of steps is odd and positive when the number of steps is even. So if we're doing it in pairs, it's positive because it's even. If it's 3 being multiplied, it's negative because 3 is odd. Now this can be generalized even further to for any polynomial function. So for any polynomial function, this is our general polynomial, the sum of all of the roots is equal to minus an minus 1 over an. That is these two coefficients. It's always over the leading coefficient, and it's the coefficient 1 before it because we are multiplying them one at a time. For the product of all of them, it is equal to the constant term over the leading term. But there's also the power, or sorry, the sign of this, which is to do with how many there are here. If n is even, this is positive. If n is odd, it's negative. So the way we can do that is raise minus 1 to the power of n, because then when n is even, this will be positive. When n is odd, this will be negative. We can also find those groups of products, like the cubic one where we had 2 multiplied at a time. Now this is not explicitly in the course, so I wouldn't expect you to have to use this one, but I will show it to you just so you've seen it, because it is a generalization of these ones. This one works in what we've just been saying. It's going to be over an, it's always over an, and then we have to work out whether it's positive or negative. So whether it's positive or negative is given by how many of these there are. Well, if there are k of them being multiplied together at a time, then k is going to be the power of negative 1. If k is even, this will be 1. If k is odd, this will be negative 1. And then on the top, we have how many do we go back. So if we go back by 1, or if we go back by 2 if we've got 2 being multiplied at a time, or if indeed we go back by n if all of them are being multiplied at a time. So if we've got k of them being multiplied at a time, the numerator is going to be an minus k. That's how many steps back we go. Now it's important to note that in the formula booklet, you are given these two formulae. You are not given the quadratic or the cubic ones. You are given these generalized versions. So you either need to be able to recognize and use these, or you need to be able to remember the cubic and quadratic ones. They are the most common polynomials that come up. Though in theory, any polynomial could come up. As I said, this is not explicitly in the course. You're only really expected to use the sum and the product of all the roots. But these formulae you need to recognize and be able to use.